This is the screencast for section 4.5, example 8. We're going to estimate change with differentials. Now, this will only be an estimate of change because change usually is not constant. So when I plug in x equals 5, I'm only getting the change at the instant 5. So if we use that change to see what's going to happen at 6, it will only be an estimate because at 5.1 the change was different. The 5.2 the change was different. The 5.3 it was changed. The change was different. So we're only going to be able to estimate the change using the differentials. We will not be able to get exact. And that's what's being represented here. Our df equals f prime of a dx. So like we talked about in the previous screencast, the change in y is the slope times the change in x, which, I mean, that just makes sense because the changes in x's would cancel out. So the change in y equals the change in y. In example 8, it says the radius r of a circle increases from a equals 10 meters to 10.1 meters. So the radius is changing from 10 to 10.1. So right off the bat, I can tell you that dr is going to be the absolute value of the difference of those two. So 0.1 meter. Use dA, so the change in area, to estimate the increase in the circle's area. Compare this estimate with the true change, delta A, and find the approximate error. All right, so first of all, the area of a circle is pi r squared. So the differential A, or the estimated change in area, is going to be 2 pi times r times the change in r. And again, that's going to be an estimate. So if we're going to find the change in area when the radius is 10 meters, we're going to plug in 10 for r, and that little change we want to monitor is 0.1. So that will be our dr value, which means that I get delta A is about 2 pi, so about 6.283 meters or square meters. Now again, this is an approximate change. To find out the actual change, I'm literally going to calculate the difference in area between a 10.1 meter radius and a 10 meter radius. So I did pi larger radius squared minus pi smaller radius squared. The absolute value of that is 2.01 pi meters squared. So not 2 pi meters squared, 2.01 meters squared. So I can calculate the error in that. The error between the two is 0.01 pi meters squared, or 1/100th of a pi meters squared. So what this problem is saying is that if I have a radius that is 10 meters long and I want it to change by 0.1 meter, that's going to approximately change the area 6.283 meters squared. Now, of course, it's going to be a little bit different than that because as your radius increases, the change in area differs. It's not the same. The actual change in area as calculated was 2.01 pi inches squared. So our difference, our error between the two was very tiny, 0.01 pi meters squared between the actual and our estimated. Then now try problem number 31. It says that the function f changes value when x changes from a to a plus dx, a and a little change in x. So we're going to find in number 31 the true change, the estimated change, and the error, similar to what we did in the example. So the true change would be finding f of a plus 0.1 minus f of just a. So I plugged in 0.1 to f of x and 0 to f of x, and I got a change of 0.21. That is the actual change. Now the estimated change I need the differential for, so I'm going to take the derivative but leave this as an expression of df equals 2x plus 2, and then that gets multiplied by dx. Now our dx is 0.1, our a value is 0, so I'll plug those in. And I get that our estimated change would have been 0.2. So if we assume that at x equals 0, the differential is changing at a constant rate, the same rate it was changing at 0, we could get an estimated change of 0.2. Now, of course, that's not it. The actual was 0.21. So our error in this case is the actual minus our estimate, and that is a mere 1/100th of a unit.